Okay, so we got to the optimization part of our unit, and this is basically one of the important part of this unit. What does the word optimization mean? The most? Could it be the least? Right? When you're optimizing, for example, on your savings, right? That means you want to save the most, right? When you're optimizing on your spending, you want to spend the least, right? So it depends on what you're doing. It's either your maximum or your minimum, right? It's either your most or your least, okay? So it depends on the scenario. It depends on what you're looking at. So for example, if I'm a company and I'm producing something, right? I want to use the least amount of product to make it, the least amount of material to make that product, okay? So if you are a company that makes tissue boxes, right? You want to try to minimize the amount of carton that you're going to use, because every centimeter that you minimize, you are saving, right? So you're minimizing how much material you're using. But at the same time, you want to optimize on your volume. So let's say if you want to have to fill something with water, right? You want to optimize on that volume, right? How much you can fit in, but at the same time, you're going to have to minimize how much material to use. So it's always something that decreases our cost, basically. Okay? So when I say the word optimization in 3D, I'm talking about when it comes to surface area, we want to minimize the surface area, because remember, surface area is the material that you use, and you're going to optimize, which is maximize the volume. Okay? So we always look at minimize the surface area and maximize the volume. Now I want you guys to go back to the activity that you guys did on Friday about the making rectangles, right? You guys made rectangles and you made squares for a certain perimeter, right? And which square or rectangle gave you the maximum area? What shape gave you the maximum area? The square, right? So with the same perimeter, right, you were able to make different rectangles, right? But the rectangle that gave you the maximum area was the actual square, okay? So that's gonna happen also when we're talking about 3D shapes, okay? If I have a prism with a 3D shape, the prism with a 3D shape, with a rectangular prism, the square prism is the one that's going to give me my maximum volume, okay? Because the square is the one that gives you the maximum surface area, okay? So when it comes to the 3D shape, we call that a cube if they're all squares, right? We call it a cube. The cube is the one that's going to give you the maximum volume and the minimum surface area. So it's your optimal shape, okay, when it comes to rectangular prism. So when we're dealing with rectangular prism, the optimal dimensions will always be that of a cube. Now, if you go back to your sheet, right, to your formula sheet, the surface area, or let's start with the volume. The volume of a cube, of a rectangular prism, is length times width times height, yes? All right, now when I have a cube, all the length, the width, and the height, they have the same side length, right? So we're going to call that side length S. So I have S, 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 S. Forget about this one on the top. Okay? So instead of length times width times height, I'm going to call it side. So it's going to be side times side times side, which is side cube, right? So when we're talking about the volume of a cube, the formula that we use is volume equals side cube. If I'm talking about surface area, if you look at my cube, I have 6 squares, yes? Each square has an area of S times S, which is S squared. So the area of this is S squared, S squared, S squared, S squared, S squared, S squared. So that's a total of 6 S squared, yes? So that means the surface area of a cube is 6S squared. Okay? So anytime I want to optimize on a rectangular prism, I'm going to pick a cube. When I'm picking the cube, the formulas that I will use for the surface area and the volume are not the one in your formula sheet. They're these ones with the volume of a cube is S cubed. The volume of the surface area of a cube is 6S squared. Are you guys okay with how they got these formulas? All right. Now the question is going to always be, they're going to give you either the volume or the surface area, and they're going to ask you to find the side length of the dimensions, basically, of the cube, and then they're going to ask you to find either the volume or the surface area, whatever they don't give you. Okay? So in this case, the volume of a shoebox is 5,000 centimeter cube. Calculate the optimal dimensions of the prism. Here's how you know. When you read that word optimal, you know that you're looking for that specific shape. I know sometimes it doesn't make sense. It doesn't make sense that you're going to have a cube shoebox. But if you're looking for your optimal, it works or it doesn't work. Like, like having a pizza, cube box pizza. Like, it's not going to work. But if that's what the question is asking you, you're solving for the optimal dimension. Okay? So, if I'm looking for the optimal dimension, that means I'm looking for side length. What formula I am going to use? What's given to me? What do I know? I know the volume. So if I know the volume, what formula do I use? The volume formula, right? So if I know the volume formula, and I know that the volume is 5,000, I'm solving for side length. What do I do to solve for side length? What's the opposite of cube? There's another name for it. It's not square, it's cube root. Okay? Because to get rid of any exponent, you do the root of that exponent. Okay? So you're going to have to do what we call a cube root to get rid of that cube. Okay? So if it was a square, then you do square root. If it's a cube, you do a cube root. If it's to a power of 4, you do a fourth root. Okay? So that root is the one that cancels the exponent. On the calculator, you'll probably see something that looks like this. Sometimes some calculators already have the cube root. Okay? Some calculators don't, so it depends on your calculator and what type of calculator you have. Okay, so cube root of 5,000, that gave me 17.1. Oh, you guys got? And what's the unit for side length? Centimeters. Okay, so you're going to have to, so put the 5,000. Second is 3.
Oh, 3. But if it's 4.
Then you put second thing 4. Okay, so basically my question is done. I just have to put my therefore statement, and my therefore statement is therefore the optimal dimension are, and then here you have to state all of them 3 times multiplied by each other, because you're looking at dimension, 3D shape, you have length, width, and height. So you're going to say 17.1 centimeter length times 17.1 centimeter, that means the width, times the 17.1 centimeter, which means the height. So this is how we state it. Are you guys okay with this? So it depends on the thing that they give you, either the volume or the surface area, right? That's the formula that you're going to start with to solve for the side length. Here's another weird example. So the surface area of a pizza box is 45,000 centimeter cube. Does that make sense to you? The unit and the thing? Surface area with centimeter cube? It should be squared. So the surface area of a pizza box is 45,000 centimeters squared. Find the dimensions of the optimal pizza box. Again, sometimes the question doesn't make too much sense, so you guys have to just live with it, okay? So what do I do here in order for me to find the dimensions of the optimal pizza box? What do I start with? What's the formula? Surface area equals to what? Yeah, because I know it's going to be a cube, right? And the surface area is 45,000, so I'm going to plug that. And then what do I do to solve for S? What's the first step? Isolate. How do you isolate? What do you do? Divide by 6. Yeah, so that's 45,000 divided by 6 equal to S squared. And then what do I do after that? And then I square root to get rid of that square that I have here. So that is going to be S equals to 86.6. So there you guys go. And the unit is centimeter, right? So therefore, the dimension of the box are 86.6 centimeter by 86.6